Let's see what are the interrupts in Symbian Operating System. The interrupt service routine on Symbian Operating System is designed as a kind of two stages. First, a short routine at an interrupt that requests the kernel to run a delayed function called DFC, and then normally the DFC takes care of the rest of interrupts and alert a user that the interrupts occurred. The motivation for this strategy is that interrupts can run over the highest priority threads, the kernel server. When this happens, it won't be much of a problem since the DFC will schedule after the kernel server. The memory management. The kernel provides a virtual mechanism environment to user process. Each process accesses its data in the same virtual address range, called the data section. The code chunked for RAM load process always appeared at 200000 in binary value. This allows multiple processes to run, each executing the same code, where the same code chunk is used for each of the processes. This reduces the RAM usage. In effect, each user process has the same kind of view. Code instructions address data using the virtual address. The memory management unit is responsible for the translation of the virtual address to the physical RAM address. Only one chunk can occupy a given virtual address range at a time. So a context switching between a different process involves remapping the chunk. The process chunk of all processes are remapped to their home address. These are in the home section, which is in the virtual address range from 08 to 0F in hexadecimal value. The kernel's data and stack chunks also reside in the home section. These are never visible to user processes. Code chunks of RAM-loaded libraries reside at the top and of the home section and have user read-only access, so that all user processes can execute code from a loaded library. A context switching between a process thus involves moving the old process chunk to the home section and changing their access permissions to preserves only, moving the new process chunk to the data sections and changing their access permissions back to the user accessible. Programs in Symbian Operating System consist of a number of processes, each of which contain one or more conceptually connected states of execution. Each user process has its own private address. Example, collection of memory regions that the process can access. A user process cannot directly address memory area in the address space of another process. Threads belong to a user process run at a user privilege level. This is a special process, the kernel process, whose threads run at the superior privilege level. This process normally contains two methods. First one is the kernel serves threads, which is initial threads whose execution begins at the rest vector, and which is used to implement all kernel functions requiring allocations or deallocations on the kernel heap. The next thing is the null threads, which runs only when no other threads are ready to run. The null threads place the processor into the idle mode to save the power. A chunk consists of the reserved region and the committed region. The reserved region is the continuous set of virtual addresses which may be occupied by the chunk. The committed region is the region in which the RAM is actually mapped. In Symbian Operating System, there are 5 chunks for the memory management. The first one is the local chunk. A chunk is local when it is private to the process creating it and it's not intended to access by other processes. A local chunk does not have a name. The next thing is the global chunk. A global chunk if it is intended to be accessed by other processes. Global chunks have names that can be used to identify the chunk to another process wishing to access it. A process can open a global chunk by name. This maps the chunk into the processor's address space, allowing direct access and enabling the sharing of data between processors. So now let's look at some sample codes on a game in Symbian Operating System. In this sample code, there is a single player mode. The game uses very simple artificial intelligence to select an element. The static method random function is used to select a random number, and the modulus operator used to derive a value between 0 and 2, which is taken as the smartphone's choice. Now let's move on to platform security of Symbian operating system. About this section we have already discussed in our first presentation, and now in this section we are only focused on the operating system 9, the security of operating system 9. Platform security is the system-wide security model introduced in Symbian OS 9. Providing an open third-party programmable platform has been an important principle in the development of Symbian OS. However, opens bring with it risk miserable software finding its way to user's device. The security model is designed to protect users from the risk while it still preserves the openness of platforms. Architecturally, platform security is a set of perceived change at all levels of the system based on a simple occupied module. While Palmer is one of the system architects who is currently responsible for platform security, processes as the unit of trust, which turns into another process. Granularly, system resources capabilities are the tokens of trust, which are required to perform actions. Data caching, which protect data from paying eyes or interfaces or both. The direct consequence of defining the process as the unit of trust is that all threads in the process share the same level of trust naturally. The goal is to protect devices users from the kinds of internationally route software or malware that plug the PC world. Symbian OS for a long time avoided some of the worst threats from malware because it was typically developed in ROM-based devices, in which the system itself cannot be corrupted. For example, it is impossible to install trapdoors or trojans in the system files because the system code is stored in an unwritable ROM memory. By design, Symbian OS also protected against some of the more trivial security holes found on other systems. Microkernel architecture helped to increase security and robustness. Since the trusted kernel is deliberately the smallest possible subset of system functions, there is a little privileged code to exploit and smaller code base to easier to review and validate. The nature of mobile devices, especially phones, also make them different from desktop systems. The physical access model is different, and also the module certifications. Symbian OS exposed a function called OEM certify module. It implemented this function gives OEM the ability to verify the trust level of a process or DLL within the OS. And the system registry stores the data about applications, user configuration settings, and performs the passwords. So because of these things, we can consider that the new operating system of Symbian is very secure. And this is our group members on programming language and design concept project. Thank you.